All right, so the last topic is dominating sets. So suppose G is a graph. A subset of vertices is called dominating if for every vertex in your graph, either the vertex is in your dominating set or is adjacent to some vertex in your dominating set. So it's somewhat similar to vertex covers. Vertex cover was a subset of vertices such that every edge was incident to some vertex in the cover. The difference here is that it's perfectly fine to have this setup here. So the circled vertex is in the dominating set, and we see for every vertex not in the set, it's adjacent to something in the set. But this is not a vertex cover because we have an uncovered edge. So we're going to let gamma of G be the minimum size of a dominating set. The reason why we'd be interested in the minimum is because it's clear that every vertex together could form a dominating set, so the maximum is trivial. For the complete graph, the minimum is 1, because if you take any vertex to be by itself, it forms a dominating set, because every other vertex is adjacent to it. If we take the cycle graph, it turns out that the gamma number is the ceiling of n divided by 3, so you divide n by 3 and round up. And to show this as an upper bound, here is the construction. Right, n is 3k plus r, where r is the remainder. It's either 0, 1, or 2. If r is 0, what you do is you take every third vertex on the cycle. So for instance, this would be this case. And the idea is that since we're taking every third vertex on the cycle, the other vertices are either adjacent right after one of the ones you picked or right before the next one. Now, of course, once you set r equal to 1, for instance, if we have a square, we see this calculation no longer works because there ends up being one more extra one. So we have to add in 3k minus 1 and find when r equals 2, that also works. And so these are 3 dominating sets of the right sizes, so that gives you an upper bound. Later, we'll prove a theorem that shows why you can't find a smaller dominating set. In these cases, the dominating sets happen to be independent sets, but to prove that doesn't happen in general, let's look at this tree. We see that any vertex doesn't form a dominating set by itself. One way to see that is if you take a vertex and delete the vertex in its entire neighborhood, there's still vertices left over. On the other hand, we do have a dominating set of size 2. And it turns out we can't form a dominating set of size 2 that's also an independent set. So here the domination number is 2. So here I want to discuss the history of dominating sets originally. So it's often referred to as saying dominating knights or rooks on a chessboard. Here we're going to discuss rooks specifically. The idea is you're putting rooks or castles on a chessboard so that every square in the chessboard either has the castle on it or is in the same row or column as a castle or rook. In other words, either every spot has a rook or can be attacked by one of the rooks that are already on the board. So we focus on rooks because in that case the answer ends up being known. It's worth pointing out that the case of knights, the corresponding domination number is not known in general. It's actually quite hard. And so in this case, it's actually the domination number. What's the connection to graph theory? If you take the complete graph, bipartite graph, and n, and take its line graph, then that corresponds to these rook configurations. And why do I take a line graph? Because remember, the line graph's vertices are the edges of the original graph, so the vertices I comma j, and then you have edges in your line graph where the edges in the original graph intersected, which means ij is adjacent to I prime j prime if the first coordinates are equal or the second coordinates are equal. In other words, these are rows and column entries in the chessboard, and 2 squares in the chessboard are adjacent if they're in the same row or column. Now, real-world applications involve ad hoc mobile networks like cell phones. So if they're trying to find a way to get data from me to you, then the way some algorithms work is they find a dominating set in the network first, like the cell phone towers, for instance, and basically they find the path from me to a vertex in the dominating set, then a path from that vertex to a vertex in the dominating set that's closest to you, and they use that to find the path. Right, so our theorem is a lower bound for the domination number. It's n divided by 1 plus the maximum degree. Note here that this solves our problem for our cycles, because then we see that gamma of g is at least n divided by 3, because the degree on a cycle is 2. And since this can be a rational number and this has to be an integer, you in general can round up here. So you could replace this with the roundup function. And so that gives us the lower bound, and we already showed the upper bound earlier, and thus for cycles, the domination number is n divided by 3 rounded up. Now, why is this theorem true? Well, we're going to use a counting argument. So we're going to count ordered pairs, where V is a vertex, U is a vertex in the dominating set, and either they're the same vertex or they are adjacent. Now we're going to count the size of this set in 2 ways. So for every vertex V, V must be dominated by something in D. And so that tells us, okay, or V is equal to U, so there's these 2 cases. So either way, for every vertex V must be the first coordinate of at least one ordered pair in X. And so thus the total number of vertices is at most the size of X. On the other hand, if we focus on the second coordinates, the size of X is this summation. For every second coordinate U, every neighbor of U could be a first coordinate, and U itself can be a first coordinate. So the size of X is the sum over every vertex in the dominating set, and we sum up this term each time. Now we can bound this from above because the size of a neighborhood is always at most the maximum degree of the graph. And so now we're summing up this constant a certain number of times, so this summation could be replaced with multiplication. So we added up this number gamma g times, so this is what we actually have. And now we see that we have n is at most this number, so we just divide. So now let's look at an upper bound for the domination number. Here, to make it work, we're going to add in an extra restriction. Let's only focus on graphs with no isolated vertices. Mainly because if you have an isolated vertex, it has to be in every dominating set. And so you can just sort of delete those temporarily, compute the domination number of the graph that's left over, and then add those ones back in. So the theorem is that an upper bound on the domination number is given by half the number of vertices. Theoretically, the way this works, you can actually even round down, and it's still true. So first we're going to look at the case where G is a connected graph. Well, if a graph is connected, it has a spanning tree. Trees are bipartite graphs, so given the tree T, you can give it a bipartition A and B. We're going to name the parts of the bipartition so that A has fewer vertices than B. And what do we see? Well, twice A is the size of A is at most the sum of the size of A and B. A and B comprise every vertex. So as a result, we see that A is at most the size number of vertices divided by 2. So it's the right size that we want. So we just need to show that A is a dominating set. Well, given a vertex V, if it's in A, we're done. So we need to look at vertices that are not in A. If it's not in A, it's in B. Then a fact we can use is that since we're looking at trees, every vertex, we're assuming we have no isolated vertices. So of course, this means that every vertex has positive degree. And since it's bipartite, every vertice's neighbors are in the other set. So the neighborhood of V and T is a subset of A. In particular, Since we know the neighborhood's not empty, this means there is a vertex in A that's adjacent to V. So this means we found a dominating set. And so now we found at least one way to find a dominating set of this size. Now what happens if your graph is not connected? Well, suppose we've got components C1 through CK. We can assume that each component has a dominating set AI that consists of at most half the vertices of that component. We're going to let A be the union of these individual dominating sets. And it's clear that A must be dominating, because given every vertex, it must be in some component. And then in that component, it's either an AI or it's adjacent to a vertex in AI. Moreover, the size of A is the size of the sum of its subsets. Each one's at most half the corresponding component. And so we add this up and we see it's half the number of vertices.